Okay, so we're on problem 13.3, C9H16O2. So this is already annotated. We'll start with IHD calculation. The IHD for this compound is equal to 2. We go through and do our hydrogen on carbon analysis, and we see that we have 16 of our hydrogens on carbon, so all of our hydrogens are on carbon. So what that tells us is what? It tells us that we do not have a hydroxyl group, so this is not going to be an alcohol or a carboxylic acid. Okay, so let's look at our functional groups. So we see that we have a peak at 173.6, which is consistent with a carbonyl peak. Remember from the previous problem, this is going to be an ester rather than a ketone because its chemical shift at 173.6 is much more consistent with an ester and completely inconsistent with a ketone. We also notice that we don't have any other alkene type functionality. So if we go down and look if we had an alkene or a carbonyl, we would be expecting something in between 100 and 200 ppm, and we just don't have that. So that tells us that we're going to have a ring as well. All right, so we have a ring and we have an ester. Sorry, this is a bit messy, but it's what I have. So at 173, we have an ester peak. We're going to go and be able to point to that in the C13 NMR. We have a peak at 173, which corresponds to the carbonyl of that peak. We also have a peak at 51.3, which is a methyl group. And that seems consistent with a methyl ester. So we're going to mark that up as a methyl ester at 51 as a quartet. And then looking back as we go to our proton data, we see at 3.67, we do indeed see a peak consistent with a methyl ester. Let's look at our tables of methyl esters. So here we can see that we have, it's consistent if we see a peak at 51, that we have a methyl ester. We would expect to see a triplet in the carbon and a larger number associated with an ethyl ester. If we go to the proton data, we can see that if we have a methyl group which is attached as an ester, we would expect, based on this table prediction, a chemical shift of 3.6 ppm, which is quite consistent with our observation. Okay, so then looking, we've got an ester. We can think about what's on the other side of this ester. All right, so we would think, again, going back and looking at our tables, we would expect that we would have a peak if we have a ester with a methyl, so we're not going to have just methyl acetate, but if we did have a methyl group, that would come at about 2 ppm. The open circles represent methylenes. That would predict a chemical shift of around 2.4, and the closed circles around 2.6 for a methyne carbon. And so we see we have a doublet at 2.2 ppm, two hydrogens, telling us that we have a methylene. This is consistent with the carbon that is next door to our carbonyl. So we have a methyl ester with a methylene attached to the ketone. That methylene is a doublet with a coupling constant of 6.4, so we can deduce from that that we have two substitutions and a single hydrogen, a single methine hydrogen attached next door, and we have a 6.4 hertz coupling between them. Okay, looking at some other elements, we also see that we have elements of symmetry in this molecule. So we have two peaks in the carbon NMR at 33 and 26, which tell us that we have symmetry involved. And we know that we have a ring structure. Finally, we're going to remember at 34.9 we have a doublet, and that's going to correspond to our methine carbon. Okay, so we have a ring, we have two symmetrical carbons and one triplet left over. So there's really only one way to put this together at this point. Okay, so basically we have This is showing a plane of symmetry running down the middle of this 6-membered ring. We have 2 sets of methylenes, a carbon at 26, and then at 34.9 we have a doublet in the carbon NMR. Okay, so then we have 6 hydrogens and 5 hydrogens filling in the cyclohexyl ring. Peak at 2.19, that is a doublet, and that completes this molecule.